In this section, we're going to be looking at exponential functions. We'll be graphing exponential functions, and we'll also be talking about some applications of exponential functions. So to get started, we should probably talk about what an exponential function is and compare it to with some of the functions that we're familiar with already, like the polynomial function. So to get started, we're used to a polynomial function. And with the polynomial function, the base was our variable. So we'd have something maybe like x cubed or 5x to the fourth plus 3x squared plus 2x plus 1, something like that. Now if you notice, each of these bases has my variable where the exponent is the constant. For an exponential function, it's just the opposite. For an exponential function, the base is a constant and my exponent is the variable. So the base is some sort of a constant, it's a number, the exponent is a variable. I could also have a variable, let's say like 2x plus 3. If you notice in this particular case, the entire exponent contains the variable. So the difference between a polynomial function and an exponential function is the location of the variable, whether it's part of the base or the exponent. Let's go ahead and talk about the graph of an exponential function. For the graph of an exponential function, we need to keep in mind that it can be one of two things depending on whether the exponent is a positive or negative value. So for this example, let's go ahead and use f of x equals 3 to the x. So I'm going to choose a few values to plot for x, and then we'll see what our output is for f of x or y. So we could choose things like -3, -2, -1, 0, 1, 2, 3. And let's see what happens. Now the important hinge point is right here when x equals 0. If I plug 3 to the 0 in here, anything to the 0 power is 1. So here's my point 0, 1. And that's going to be an important point. Now if we plug in a 1, I get 3 to the first is 3. And you'll see almost right away that this is going to jump right off of this graph. If I plug in a 2, 3 to the second or 3 squared is 9. And I can't even do 3 to the third. 3 to the third would be 27, but it kind of runs off the page here. Now what about -1? 3 to the -1, I'd flip the exponent because of the negative exponent, it would be 1/3. So at -1, I'd be somewhere down here at 1/3. Now at -2, I'd have 3 to the -2, which is 1 over 3 squared, which is 1/9. Now 1/9 is closer to the x-axis. Now 3 to the -3 would be 1 over 27. And that's even closer. So as these numbers get closer and closer toward -infinity, I'm getting closer and closer to the x-axis, but I'm never crossing it. So this is a positive exponential graph. So what we want to think about here is how the effect of the graph works in terms of a horizontal asymptote. So if we look at this, the graph of the exponential function f with this base of 3, and this will be true with any constant base, approaches but does not touch the x-axis. So it gets very, very close to the x-axis but does not touch it. Now this axis, the x-axis, has the equation y equals 0. So it is the x-axis, but the equation of the x-axis is y equals 0, and this is called a horizontal asymptote. So I get very, very close to the axis, but I'll never touch it or cross it. So for instance, if I went to -100 here, 3 to the -100 would be 1 over 3 to the 100th, which is a huge number in the denominator, but overall fraction is very, very close to 0. There's no number I could plug into this to get 0 back out or to get a negative number back out. So this is an example of an exponential function. This is a growth function. So it's growing exponentially. Let's go ahead and look at another example too of an exponential function. This one's going to be a little bit different. Instead of 3 to the x, let's look at this as 3 to the -x. Now let's think about how else 3 to the -x looks. If I flip this, this would be the same as 1 over 3 to the x, or I could write this as 1/3 quantity to the x. because when I distribute the x to the numerator, I get 1 to the x, which is 1, and then 3 to the x. So all three of these things will produce the same graph. So let's go ahead and look at some values here that we could plug in. These are going to be a little bit trickier because we need to remember that everything's in that denominator now. Basically what ends up happening is everything spins opposite. So what was 3 when I plugged in was 27. Now what I'm going to have to worry about is what happens with our negative 3. So it would be 3 minus a negative 3, which is 3 to the third, which is 27. So I get 27 here. Now you can check these as well. If I plugged in a negative 2, it would be minus a negative 2. 3 squared is 9. This would be a 3. This one stays that nice little hinge point. This would be 3 to the negative 0, and of course that's the same as just 3 to the 0, which is 1. If I plugged in a 1, this would be 3 to the negative 1, which is 1/3. 3 to the negative 2 would be 1/9, and 3 to the negative 3 would be 1/27. So if you notice, from what's happening up here to what's happening down here, everything is just swapped. So let's go ahead and plot a few of these points. This point of 0, 1 is going to be important for both these graphs. So there's 0, 1. Now here if I plug in a 1, I'm at 1/3. 2, I'm at 1/9, and you can see I'm getting closer and closer and closer to this x-axis again, but never crossing it. Now if I plug in a negative 1, I'm up here at 3, and at negative 2, I'm up here at 9. So this is just the mirror image of the exponential growth function, and this is called exponential decay. So if you've ever heard of carbon-14 dating of ancient objects or ancient artifacts or ancient bones, this is what they're using, is this idea of exponential decay to predict the age based on the half-life of carbon-14. So this is exponential decay. Now, we know this is going to be exponential decay because I have a negative exponent, or it can be rewritten in a negative exponential form. This also has a horizontal asymptote at y equals 0. This is the equation y equals 0. And it gets closer and closer to the x-axis, but actually never crosses it. So these are some pretty interesting characteristics about an exponential function. A couple other things about exponential functions. Let's talk about the domain and the range. The domain is all real numbers. There's no restriction for what I can plug in. Now the range is interesting. I never touch the x-axis. Now remember, range is vertical, and I never touch the x-axis, so I have to have a parenthesis, not a bracket, and then this cruises off toward positive infinity. So this is the domain and the range for an exponential function. Now if I make transformations to the exponential function, like add 4 and subtract 6, that's going to change. But these are just for the basic exponential functions, such as 3 to the x or 3 to the negative x, and I could replace these values with anything I wanted here. So those are some basic characteristics of exponential functions. Well, let's go ahead and look to see how we would graph these using your calculator. So let's go ahead and pull in calculator here. Now when we're graphing exponential functions, we always want to make sure that we keep in mind our constant is the base and the exponent is my variable. So for instance, I could graph 3 to the x like we were just doing, so 3 exponent x. Now I always have to be really careful that the entire exponent is correct, so always double check that. Let's hit graph, and we may need to change our axes here a little bit. Here's my increasing graph. Now it looks like it's touching the x-axis here, but that just has to do with the fact that it's getting very, very close, and our calculator's not good at approximating 1/3, 1/9, 1/27, 1/81, etc. Now let's go ahead and look at our table very quickly, and let's see if something interesting is going on. As we get lower and lower values here, -10, etc., you can see that I'm getting close to 0. This means 6.3 times 10 to the -7. So that's a 6 and a 3 with 6 zeros in front of it and then a decimal spot. And if you keep scrolling, you can just see that these get closer and closer and closer to 0. Now at some point our calculator might have to actually say, okay, I give up, it is 0, but you have to remember that it's getting closer but never touching or crossing at 0. So let's go ahead and pull this graph in, and then actually, you know what, let's go ahead and graph the other negative exponential graph here as well. So for our negative exponential graph, let's go ahead and do 3 to the negative x. 3 exponent negative x. Now if your calculator uses parentheses, you need to make sure the negative and the x are in the parentheses after you use your caret key. So let's go ahead and graph, and we'll see their first graph, our positive exponential, and here's our negative exponential. And again, it's getting closer and closer to the x-axis but never crossing. So we can see they have the same domain from negative to positive infinity, and the same range starts right above 0 and goes off toward positive infinity. So the way I can remember this is going toward positive infinity, it's growing. So this is a graph of 3 to the x. This one is getting smaller and closer to the x-axis, so I can kind of remember that it's going toward negative values. It never actually gets toward any negative values, but it's going toward negative values, so it's 3 to the negative x. So these are some important things to keep in mind when we're talking about exponential functions, is what that graph actually looks like. Now, a lot of times when we're working with the exponential functions, we're working with a specific base. So an important base that we work with, we just worked with 3 for our base, but one that comes up a lot is e. Now this is called the natural number, and it's a constant, just like pi represents 3.14159. E is approximately equal to the constant 2.718. Now on your calculators, you have an e key. So over here on your calculator, the e is right above the division sign. Okay, so right here above the division sign would be our e key. So let's go second quit. And if we wanted to see e, we'd go second the division, and we'd see our e showing up here, and then you could use your exponents, etc. Now no matter what my base is, it could be 1, it could be 10, it could be 20, to the x, it's going to have this general shape. It might grow faster or hit the x-axis harder, but it's going to have the same general shape. Same thing with here, if I have that negative exponent, it's going to hit that axis a little faster as that negative exponent gets toward positive infinity, but it's the same basic idea here. Now the natural number e is approximately equal to 2.718. You usually won't ever have to type in 2.718. You just use the e key on your calculator. This is used in a lot of financial calculations. So for interest on mortgage rates, some things like that, this is very common to use that natural number e. So if you wanted to graph this on your calculator, you could. Or we could just look at a graph, let's say e to the x. So the graph of e to the x, if I plug in 0, e to the 0 is 1, so there's that important hinge point. Positive exponent, so I know it has growth. Now y equal e to the negative x, I can look at that important hinge point. If we plug in a 0, I get a 1 back out, and because my exponent is negative, I have decay occurring. So these are just a quick hand sketch of what's going on here. Now a lot of times in your homework set, you'll be asked to graph the transformations. Now all the transformation rules that you've already learned from other sections are also true for this section, but let's review them very quickly. Now one of the transformations we've already looked at, but let's go ahead and formally state it again. So what I'm going to do for these transformations is I'm going to just use 3 to the x as my standard or my parent function and work on the transformations from there. So my parent graph is going to be y equal 3 to the x. Now it could be any base right here. It could be 2 to the x, it could be 7 to the x, it could be 8 to the x. It can't be 1 to the x though. I forgot to talk about that, but we'll talk about that right after we get done with transformations here. 1 to the x is not an exponential growth graph, it's a constant. But from this parent graph, we could have something like y equal 3 to the x, and then outside of the x, in the base again, we could have a plus 1. This is a vertical shift. up 1 unit. Now we could also have something, let's say, like y equal 3 to the x minus 5. This would be a vertical shift down 1 unit, or sorry, down 5 units. Okay, so this works just like my other ones. If it's on the outside of the original function, it's a vertical movement. Let's go ahead and look at another example, y equal 3 to the negative x. Okay, so this is not on the outside of the 3, this is within the argument of the 3. So what this is a reflection across the y-axis. Now if we had the negative on the outside, a negative 3 to the x, now we have to be careful with this. This exponent x only goes to the 3, it doesn't go to the negative sign, so only the 3, and then you negate your answer. This is a reflection across the x-axis. Okay, now we also can have two other ones that we'll talk about. We could have y equal 3, let's say, to the x plus 1, and then let's also have y equal 3 to the x minus 4, let's say. Well, because it's within the argument, we know it's going to be horizontal. So this is going to be a horizontal shift to the, now because it is within the argument, it's always opposite. So not shift to the right 1 unit, but shift to the left 1 unit. And conversely, this would be a horizontal shift to the opposite of what we think. We think we'd mean left, but because it's within the argument, you do opposite, to the right 4 units. So these are the basic transformations that we're going to be looking at in your graphs. And the best thing to do when you have a transformation is plot a couple points, see what it looks like, graph it on your calculator, and see what you can come up with. But being able to plot points is going to be pretty important. Now, I brought up something that I should have brought up a little bit earlier, but what about the function y equal 1 to the x? We talked about a 3 to the x, a 10 to the x, a 5 to the x, or y equal 1 to the negative x. What do these graphs look like? Well, we know 1 to any power is just going to be 1, so this is just a horizontal line. 1 to any power is still just 1. So both of these are just horizontal lines. No exponential growth or decay. And they're horizontal lines that go through y equal 1. So this is y equal 1. So this is the graph of y equal 1 to the x. And this is the graph of y equal 1 to the negative x. So 1 is the exception to the rule of exponential growth and decay. The base can be anything, and I'll show exponential growth or exponential decay if the exponent's negative. But when my base is 1, I just have a constant function. So this is called a constant function. It's not increasing or decreasing. So that's kind of our one that we need to remember here. Let's go ahead and pull in a question from my math lab and see what we can do to evaluate. So for this graph, it says match the graph, so we're matching this graph over here to one of these functions over here. Well, the first thing I would notice is this is not exponential growth, this is exponential decay. And because it's exponential decay, I need to have a negative x in the exponent. So if you notice all these bases are 3, I think that this graph is going to look like something like 3 to the negative x. It might have something else going on, but I think this is its basic shape. So right away I can throw out 3 to the x. I can throw out the negative 3 to the x because this would reflect down across the x-axis. 3 to the x minus 1, that's going to be exponential growth. Now it could be this one because of the minus x. It could be this one because of the minus x. It could be this one because of the minus x, not this one because of the positive x, and not this one because of the positive x. So let's go ahead and try and use one other strategy to try and figure out what's going on here. Now remember, before this was transformed, it came through this graph or this point right here. And now that it's been transformed, it looks like to me it's moved 1 unit to the right. So a horizontal shift to the right 1 unit, I'd have to think about, okay, that's going to be in the exponent is the horizontal movement, and going to the right, so I'm going to have an opposite here. So I'll kind of do the opposite of what I expect. So let's check a few of these points. If I plug in a 1 for my value of x, this says I get out a 1 for my value of y. So if I plug a 1 in here, 3 to the negative 1, that's equal to 1/3. So it can't be this one. This one, if I plug in a 1, I have 3 to the negative 1, which is 1/3, and this says to negate it. So it looks like I'm left with 3 to the exponent 1 minus x. So I think our answer here is E. But just to be sure, let's go ahead and graph this as well. So 3 exponent 1 minus x. So in graphing, you use your y equal. So I have 3 exponent, and we decided it was 1 minus x. So let's see if this is right or if we need to choose a different one. So it should be coming swooping down. We'll see how far over it goes. Okay, so there's that point. Over 1, up 1. So if I plug in a 1, I can get a 1 back. Now this other graph that's graphing is, if you remember back in my y equal, I should take that out of there. I had the second graph down here, so let's go ahead and delete that one. Just graph the original. So here it comes. If I plug in a 1, I get a 1 back out, so this looks pretty reasonable. It looks like it's crossing up here around 3, which my graph also looked like it was crossing around 3. So let's go ahead and pop this into our lecture and see how it compares with that graph. Okay, so it looks like it fits. You know, we could elongate the scale if we needed to, but for the most part it looks like it fits perfect. So 3 to the 1 minus x. Now this looks a little bit different than we'd usually expect, because this looks like a positive 1, which seems like it should be a shift then to the left, and this is shifting to the right. But what's happening here is if we look at this exponent, 3 to the 1 minus x, let's go ahead and rewrite this negative x plus 1, so all we did was change the order. Then if we factor out a negative 1, we'd be left with x minus 1. So the negative 1 distributes but creates a negative x, and the negative 1 times a negative 1 creates a positive 1. So now you can see we have our reflection and our shift in the exponent minus 1, which would translate to opposite direction as shift of a plus 1. So plotting the points is going to be really helpful because this is a bit of a tricky business. Let's go ahead and look at another example of an exponential function that you'll be running across and in your homework. And I'm actually going to run through the problem with you live in my math lab so you can see how these work. So it asks us to graph e to the x plus 5. Notice the plus 5 is not in the exponent. So this is an exponential growth graph, and then I shift it 5 units up vertically. So first of all, we need to grab the tool, and if we just click on the screen, I can go ahead and do all these transformations right here. This is a vertical shift up 5 units. So that's really our only transformation here. So if we click off of that, notice that it goes up 5 units. Now also, after we've graphed the function, we also need to find its domain and range. Now one thing that we can't see really clearly here is there's a dotted line. There's this little dotted line that represents this horizontal asymptote, and this horizontal asymptote is at y equal 5. It's at y equal 5 because it used to be at y equals 0, and then I shifted up 5 units. So let's go ahead and check this answer and then kind of get to the next part here. So now it's asking for the equation of the asymptote. Now the asymptote it's looking at is this horizontal one. So you want an equation, so you need y equal 5. You can't just put in a 5, you need the equation there. Now the domain is all real numbers because there are no restrictions on what I can plug in, because I don't have a denominator and I don't have a radical that I need to worry about. So the domain here is all real numbers. Now the range is what's changed. Usually the range for an exponential function goes from just past 0 toward infinity. But now, since my whole graph has shifted up, it's going from just past 5 to infinity. Now it never actually reaches 5, so I have to use a parenthesis, 5, comma, off to infinity, close parenthesis. And so that's kind of the type of problem that you'll run into when you're working with some of these. And again, when we're working through these, just make sure you follow the directions step by step, and they're usually pretty straightforward. And then another thing that you can do is always graph everything on your calculator as well, so you can verify any of the results. So let's shrink this down so it fits. And then you can see your graph here. Now, while we're at it, let's go ahead and graph e to the x plus 5, just so we can kind of compare that with our calculator work. So grabbing our calculator, let's pull that in. Now on this one, let's be really careful that x is my exponent and the plus 5 is not in my exponent. So y equal, let's clear out our old one. Now here's my e graph. So that's the second, this one on mine is above my division, exponent, e to the x, and then I have to make sure I move out of the exponent to do my plus 5. So let's go ahead and graph. Now this is not going to show me my horizontal asymptote. It doesn't even look like we can see any of the graph, and I think what's happening here, if you remember, the graph is above 5, and here I'm right at 5. So let's go ahead and change our window. So on the y-axis, my y max, let's go up to, let's say, 25. And you can choose any value you want. I just chose 25. So here's 5, that horizontal asymptote, and here's my graph. So this looks reasonable. So let's go ahead and pop this into our lecture and compare it. Now if they look more steep or less steep, the problem is my scale is different. Okay, so they look different because of the scale, but the same basic graph is identical. So it's going through at 6, it looks like, and it's going through at 6 right here as well, and then it's increasing, and I have this horizontal asymptote at y equal 5. So those are some of the types of problems that you'll run into for graphing. Now some of the other problems that you're going to be looking at are going to be application problems. So let's go ahead and look at some application problems, and we'll look at kind of some of the different criteria for the application problems, and then also look at how we can use our calculators to help solve the application problems. And like we talked about at the beginning of this unit, or the beginning of this homework, a lot of the application problems for exponential functions are in finance areas, so like banking and business. So let's go ahead and look at those to give us a start. There's two problems, or two formulas, that we're going to be using most of all. So both of these have some sort of growth factor. So if you invest money in an account and it grows, then these are kind of some of the formulas that we'll want to go after. So our first one is A equals P, in parentheses, 1 plus R over N to the NT. Now this definitely looks exponential because I do have this exponent, but we need to go ahead and define each of these values. So A is equal to the balance in the account when P dollars are invested. So when we say P dollars are invested, this means principal. That means the initial amount invested. So A is the balance in the account when P dollars are invested. So again, P stands for principal here, at an annual interest rate Now this annual interest rate is R, and when we use R, we use a decimal form. So if I have 7% interest, I use 0.07, etc. Okay, so A is the balance in the account when P dollars are invested in an annual interest rate R that is in decimal form for, now we have a couple of other variables here. we have the variable t, and we also have the variable n left. So before we can get started, let's go ahead and talk about t. T is the amount of time in years. Now the only variable that we haven't talked about is n. N is the number of compounding periods. This means how many times per year will this be compounded. Compounded means the interest is added back to the principal in the account, and then the account continues to earn interest on the principal and the compounded amount. So there's different compounding periods. So there's daily, and if I compound daily, n would equal 365, so once a day. I could be compounding semi-annually, and when I talk about semi-annually, what we're trying to get at there is how often that is compounded is twice a year, so the number of compounding periods is 2. We could say that it's compounded quarterly, and if it's compounded quarterly, quarter 4, so I have 4 times per year. And then, this is kind of an interesting one, if it's compounded continuously, I don't have a value for n here because it's compounding all the time. I need to switch to a different formula. And the formula that we're looking at here then is going to be a little bit different. It's going to be a little bit more simple. And it looks like, I think we use the same variable a, but let me double check here. So I have a equals p e to the RT. So a equals p for my principal, e for my natural number e, r for my interest rate, t for time. So this is for continuously compounding interest. And this usually is where we can earn the most money, is for interest that's continuously compounding interest. If I only compound annually, n only equals 1, so I guess I can add another one up here. Annually, n is once per year. Daily is 365 times per year. Semi-annually is twice per year. Quarterly is 4 times per year. So you kind of have to look at the problem and say, okay, what do I have? Do I have daily, semi-annually, quarterly, or annually? Or do I have continuously? And then based on those, you can choose which formula you're going to use. So let's go ahead and pull in an example from my math lab and work through it. Now these problems can get a little bit long, depending on how many times they want you to compound and how many ways they want you to check. But they're pretty straightforward, so I think once we run through one example, you won't have any troubles with the rest. Okay, to get started on this problem, first of all, it says use one of these two formulas. So remember, this one is for continuously compounding, and the other one on the left is for when we are compounding quarterly, semi-annually, monthly would be another one that we could look at as well. Actually, let's go ahead and add monthly up to this list. So if we have monthly, that would be n equal 12. Okay, so what is the accumulated value if the money is compounded semi-annually? Okay, well, we have these two formulas. Now if we switch back up here, A stands for the balancing the account after the investment is made. So another way that we could look at this is A could stand for the accumulated amount. It's the balance in the account after my investment has been made. So what we're getting started with here then is that A is my accumulated amount, that's what I'm looking for. P is my principal. Well, it says right here 15,000 is my principal. And then I have 1 plus. R is my interest rate, so that's 5%, but I write it in as a decimal, 0.05 over n. Well, we'll talk about the n here in a little bit. and then I have an exponent of n, and then t is 4 years. Now for this example, when I say semi-annually, that means I'm going to look at this accumulating or compounding twice per year. So a 2 would go in for my formula for n up here. So when you plug this into your calculator, you have to be really, really careful. There's a lot going on here. So let's go ahead and pull in the calculator. And let's keep in mind 15,000. So let's start with second quit here because I don't need to graph this. So I'm going to have 15,000. I'm going to open my parentheses. 1 plus r was 0.05 divided by n was semi-annual, so it's 2. And then I have my exponent. Now if you have a caret key that doesn't jump up into your exponents, you need to put parentheses here, because now I need to make sure I multiply by my parenthesis in my exponent of 2 times 4. And I know 2 times 4 is 8, and I could just put an 8 here, but I just want to kind of type out what everything is for this particular problem. So here I get $18,276, and if I rounded this to the nearest cents, that would be 4 cents. So this is how I put this into the calculator to figure out how much this value actually is. So let's go ahead and pop this back into our notes, and again, this is for semi-annual. Now it says to round this to the nearest cent. Now semi-annual means twice per year, so that's where the 2 comes in. And if I round this to the nearest cent, that would be $18,276.04, because the 3 does not round the 4 up to a 5. So for semi-annual, my answer would be $18,276.04. So that's part A. Part B, so we're done with part A, compounded semi-annually. Let's go ahead and look at part B. How would this change for compounded quarterly? Well, compounded quarterly, nothing has changed. The only thing that's changed is in my formula, the amount of compounding periods. So I still have A equal 15,000, 1 plus 0.05. Quarterly compounding means n equals 4, and this is to the n times t. So n is 4. Now t is 4 years. So this didn't change up here with this 4. The only thing that changed was the compounding periods. So let's go ahead and plug this into our calculators and see what we get back out. We're going to plug it in the same as the last one. Now I wonder, I was going to try and see if we could go back up and edit this one. Yeah, we can. So on mine I can go back up and edit, or at least I think I can. I guess not. So let's go ahead and type it in again. 15,000. 1 plus r is 0.05, over 4, because I have quarterly compounding, exponent. Now in my exponent, I don't have 2 times 4, I now have 4 times 4, because I have quarterly compounding for 4 years. So the amount accumulated is $18,298.34. So it's the same amount invested, but when I compound my money more often, I earn more interest. So compounding more often earns more interest is kind of one of the takeaways from this. So the amount that I have accumulated here for quarterly would be $18,298.34. And again, the 3 does not round this up. So same amount of money invested for the same amount of time, but when I compound quarterly, I earn just a little bit more interest. It looks like maybe about $21, $22 more interest. So that's part B. Part C is compounded monthly. So I do the same thing, except I would replace the 4 and the 4 right here with the 12 because it's compounded monthly. Let's go ahead and skip ahead to compounded continuously. So compounded continuously. Now, if I compound twice a year and I get more interest if I compound quarterly, and I would have gotten even more interest if I would have showed the work for compounded monthly, compounding continuously, which means constantly, should really yield a lot more interest. So I have A equals P e to the RT. Now E is just the constant, 2.718, but you have an E button on your calculator. My principal P is 15,000. E to the R, my R is 0.05 is my interest rate. And T is the amount of time, and that was 4 years. So when I'm working this type of problem, I don't take 15,000 times E. I take E to the 0.05 times 4, and then times 15,000. Now my calculator knows my order of operations, so it will kind of help me keep track of this. So I have 15,000 E. Now with my exponent, again, you should have parentheses around this if you don't have this exponent key that puts you up into the exponent as opposed to just a caret. And my T was 5 years. Oh my goodness, that was quite a difference here. So now I'm up to 19,260. So that was quite a nice boost. Compounding continuously makes a huge difference. Now, when you look at, let's say, a credit card statement or a bank statement, a lot of times it will talk about how it compounds. And of course, as you can imagine, a credit card statement is going to compound continuously because they're earning interest continuously. So they're earning more interest by charging you more interest with that compounding. Okay, wait, I think I see a mistake here. If you notice right here, I put in 5 for 5 years, but it should be 4, because up here in this formula I had a 4. So let's go ahead and go back into the calculator. Now our number is going to be a little bit smaller. I thought that was too good to be true. It was a very nice rate of return. E to the 0.05 times 4 years. So let's put in a times 4. It's going to be less. Oh, my exponent didn't go through. Having bad luck today. 15,000 times E is my exponent to the 0.05 times 4. Okay, so from all my mistakes that you've seen here, you can see how important that it is that we are very careful about how we enter everything into the calculator, because if we enter bad numbers will come back out for sure. Okay, so let's go ahead and get this in correctly. This is the corrected values. So if I compound continuously, I would expect to see $18,321 and then 4 cents, because the 1 will not round the 4 up, so 0.04. And that's my correct answer. Be really careful about how you plug these into your calculators, because clearly it's easy to make a mistake. Now the other type of problem that you have will be kind of a story problem that's saying, guess and check. What happens if we invest this amount of money and we have compounded continuously, or we have compounded quarterly, and for a comparison point? And sometimes the results can be a little bit tricky. They might not exactly come out to be what you'd expect. So you always need to run the numbers. You can't just take a guess at these. And these are really good test questions too. So it's good to practice them. So for this one, it says, suppose you have $13,000 to invest. So we're starting off with $13,000 to invest. Which of the two rates would yield the larger amount in 3 years? So we know T equals 3, and we know P equals 13,000. So we have two options, 8% compounded daily. So 8% compounded daily. Or 7.88% compounded continuously. So we need to run two different formulas here. So let's go ahead and start with our first one. The formula that we're going to use is P 1 plus R over N to the NT. So my principal will be the same, it's 13,000. My interest rate for this example is 8%, which is 0.08. The number of compounding periods, if I go daily, I would use N equals 365, because there's 365 days in a year. Now my exponent is N, the number of compounding periods, 365, and then T is the number of years, and T is 3 from up here. So I'm just going to go ahead and plug this into my calculator and see what I get. So I have 13,000 parenthesis 1 plus r. Now r is 0.08 for my first example. I'm compounding daily, so I have 365 compounding periods. My exponent, and remember, if you have a caret key and it doesn't put you up into the exponent, make sure you have parentheses here. I need 365 for my number of compounding periods times 3, because I have 3 years. So the amount that I would get at the end of that scenario's investment period would be this 16,525. So that's for this scenario, $16,525.80. Okay, now this one on this side, I'm compounding continuously. So for continuous compounding, I have P e to the RT. Principal is the same, it's 13,000. E is my exponential, my natural number. R is my interest rate. 7.88% would be 0.0788. That's what it would be as a decimal. T is the number of years, and I think on this one we had 3 years. So let's go ahead and plug this into the calculator. So I'm going to have 13,000. I'll have e to the r, so I have an exponent. My r is 0.0788 times 3 years. So I have a different amount for this one. I have $16,466.85. Now the question was, which one would yield the larger amount in 3 years? So we use the same time period. Well, we can see pretty clearly that this is the larger number. So this is larger. So we'd have to say, therefore, the 7.88% account compounding continuously yields the larger amount. Now this is kind of surprising in a way, because if you just took this at face value, you might say, oh, 8% is a larger interest rate, so it will yield more. But it really doesn't, because of the difference in compounding. But at some point, it could yield more if the interest rate over here was low enough. So that's why you always have to check. There's one other problem I want to look at, and we won't actually do the whole problem, but I want to show you a quick pitfall that you have to watch out for when you're plugging in values into your calculator. So in this one it says the 1982 explosion at a nuclear lab sent about 1,000 kilograms of a radioactive element into the atmosphere. This is the function right here that describes the amount, f of x, so f of x is the amount in kilograms of a radioactive element remaining in the area x years, so x represents years after 1982. If even 100 kilograms of the radioactive element remains in the atmosphere, the area is considered unsafe for human habitation. Find f of 40. So let's go ahead and start with f of 40. Now for f of 40, that means x equal 40. So what does this look like? So this looks like 1,000, 0.5. Now up here in my exponent is the 40 over 30. Now, when you're going to do this problem on your calculator, you can't take the 1,000 times 0.5. You have to do the exponent first. So this piece I have to do first. And when I get the answer, I can multiply by 1,000. Or if you would like, we can just plug the whole thing into your calculator in one fell swoop. So it'd be 1,000. Okay, and then I'm going to put in my times sign. I have 0.5 exponent, and if you don't have the caret key that actually puts this in the exponent, you need to make sure you use parentheses. 40 divided by 30. Okay, so again, we don't take the 1,000 times 0.5, we do this piece first with the exponent, because order of operations say PEMDAS, parentheses and exponents come before multiplication and division. So we have to be careful about how we plug that in. So let's go ahead and see what this number is. It says type an integer. Just looking at our directions here. It says type an integer or a decimal rounded to the nearest tenth. Okay, so if we're going to round this to the nearest tenth, this would be 396 point. This 5 would round the 8 to a 9. So my answer here would be 396.9. Now let's think about what this means. 396.9. Well, 396.9 means the number of kilograms that are remaining X years after 1982. Well, X was 40, so 40 years after 1982. So that would be 82, 1982 plus 40, 92, 2002, 2012, 2022. So this is the amount of radioactive elements remaining in the atmosphere in 2022, I think we just said. So that's what we're trying to do, is to compare these and then come up with a decision here. And I'll let you guys do that part. Okay, so coming up with the decision part. So when you're working on this section, just remember we're looking at exponential growth and decay. The application problems were usually from an investment viewpoint would be one way to look at it, or some of these radioactive type problems. Remember that you have to be very careful when you're entering these into your calculator, because order of operations does matter here. If you have any questions about the lecture, you're welcome to bring those to class, stop by the Math Center, come by my office hours, but let us make sure that we get those questions clarified for you. Good luck on this assignment.